So before we get started, I'm going to leave this list for travel things at the front here. So please come up and put it down. And the time we want is the time you want to get to the airport or the train station, not your flight time. Okay, so it's up to you to estimate how much time you need. Right? All right? Thanks. All right, so the second talk this morning with Michal P from Gent. He's going to tell us about resurgence in relativistic hydro. Thanks, Michal.
Hello, everyone. First, I want to share my happiness with the snow. I mean, I think it sort of doesn't act in favor of the conference, but it's not that often that I see snow myself, so that really uplifted my spirit. And today, I want to talk about a series of works that date back to the 2013, probably, that culminated, at least on my side, with these two papers written with Alex Cervantes, who's there in the audience, with Michał P, who's there in the audience, with my former PhD student, Victor Svensson, and Ben Witters, who might be in the virtual audience, but spoke also here before. So let me start with a bit of a context. So the motivation for whatever I want to tell you, at least like a vast part of what I want to tell you, comes from ultra-relativistic nuclear collisions at RIC and LHC accelerators. So these are very violent non-equilibrium processes in QCD, in the theory of strong interactions, that according to our best phenomenological understanding, create, after some time from the collision of two nuclei, a deconfined phase of QCD, the quark-gluon plasma, and you can see it here, that is characterized, crucially, by a very small value of the shear viscosity transport coefficient of the order of 1/4 pi, that is the value relevant for a whole class of holographic quantum field theories. So basically, in my talk, for most of it, I want to talk a bit about what does the theory, I mean theoretical physics, as of this year, tell us about the emergence of the quark-gluon plasma in experiment. And of course, an important role is going to be played by resurgence, and that's why I'm talking about this to you. So, of course, it's very hard to solve for the dynamics in QCD following a nuclear collision. I mean, it can be done in a series of models, approximations of QCD dynamics, for example, starting with strong classical fields, through some kinetic theory, through hydrodynamics. But it's not that you can get the full answer, say, for the energy momentum tensor of your matter in one go in QCD. So what I want to discuss is, instead of talking about a multi-stage process in different models, in this talk I want to focus on one model and try to see, or like one model at a time, and try to see what does such a model predict when it comes to the time development of the energy momentum tensor operator, the expectation value of the energy momentum tensor operator. So the model that I want to discuss most is holography, so ADS-CFT, in which one replaces QCD by a certain strongly coupled family of gauge theories with large number of microscopic constituents. And you can solve these theories using gravity, using solving Einstein's equations with negative cosmological constant and matter, if you wish. And a particular result is given by this plot. So what we see here is time. And this time I devote by W, and you're going to learn what W really stands for. And on the y-axis, you see pressure difference. And we're talking about non-equilibrium processes. So the energy momentum tensor is not necessarily of the form of equilibrium, right? In general, it has a complicated time dependence. And indeed, like what you see is that this pressure difference for the whole evolution is non-zero, which means that the system is anisotropic. And indeed, collisions are anisotropic, right? Like here, we have a collision axis, and we have two remaining spatial directions. There is an anisotropy between these directions. And what we see is that there is some transit period of evolution for 3 different non-equilibrium states. And then at sufficiently late times, from around time equal 0.6 in particular units, there is a universal behavior emerging that is shared by these states as well as many other states and continues at much later times. And you can look at it more quantitatively, and you can perform a fit. And if you perform a simple fit at late times, you're going to see that this tail here is a simple power law. It's like 1 over W with some well-defined coefficient that you can determine numerically. And if you're more picky, you can try to determine perhaps like subleading corrections, power law corrections. But now, like if you look at what's happening earlier, what you're going to find is that these transient effects are exponentially suppressed in W. And there are also oscillatory parts, right? Like you see here some clear oscillations, right? So there are exponential, these exponents have, in general, complex parameters in them. So basically, what I want to talk about is understanding, the relation between this bit and that bit using asymptotic techniques, and trying to see to what extent we can generalize it to perhaps much more interesting setups than the dynamics we consider in holography in 2011. So this is the motivation. The underlying physics for the beginning of my talk is the so-called Bjorken flow. So this is the space-time diagram of the collisions. So like you should think about this diagram as literally representing what you saw here. Sorry. So the collision happened at some position along the collision axis at initial time. And then in the future light cone, there's going to be non-equilibrium matter that was created by this violent process. And of course, in general, the dynamics is going to depend on where you are along the collision axis and where you are in time. So in general, this process is going to depend at least on 2 space-time coordinates. And perhaps, like if you look at more realistic situations, like there's going to be also dependence on the transverse coordinates that I don't show. So that's actually very hard to solve, very hard to analyze in a quantitative way. So the idea that goes back to pioneering work by James Bjorken in 1982 is to assume that the dynamics is the same in all longitudinally boosted reference frames. So in other words, the dynamics is not going to depend on basically space-time rapidity. It's going to just depend on the proper time that elapsed after the collision. So the physics is going to be the same on all curved time slices given by the surfaces of constant proper time. And this is a beautiful thing from the point of view of analyzing the dynamics in detail, because that basically means that whatever we're going to do is not going to depend on proper time, on the time and position separately. It's going to depend on them through a single variable, which is this proper time. So that's basically the kind of dynamics from behind the plot that I showed you in holography. And now I want to talk about how to understand like this endpoint, this emergent universality. And the way to understand it is in terms of relativistic hydrodynamics, and that's basically a notion from the subject of the talk. And in relativistic systems, like nuclear matter at Rig and LHC, energy and momentum are encoded in the energy-momentum tensor operator. And general energy-momentum tensor has, it's a symmetric operator, so it has, in general, 10 components. But it's also a conserved current, so there are 4 conservation equations associated with this operator. And relativistic hydrodynamics, as an effective field theory in modern understanding, is built on the premise that if we wait long enough, the number of degrees of freedom encoded relevant for the dynamics that can be thought of as independent components of the energy-momentum tensor is going to drop from 10 to a lower number. And indeed, at very late times, one would expect local thermalization to occur. And if this is the case, then the energy-momentum tensor is going to take a form of the equilibrium one, but now locally at different positions in space and time, such that the local temperature and the local velocity basically by definition depend on where you are in space-time. And the stress tensor of such a form, expressed in terms of in physical number of dimensions, 4 functions, 3 components for velocity, and say local temperature, defines perfect fluid hydrodynamics. So a theory of fluids in which there is no dissipation, in which there is exactly conserved energy, the entropy current. So clearly, dissipation is important in physical systems, and in particular, it's crucial for nuclear collisions because the physics of dissipation is what allowed to clearly distinguish between weakly coupled and strongly coupled models of nuclear collisions at RIC and LHC. And in the context of relativistic hydrodynamics, the dissipation is encapsulated in terms of corrections to this perfect fluid stress tensor. And to the leading order in derivatives, so we're doing effective field theory, so we're going to be adding corrections in derivatives of fluid variables. The dissipative terms are basically 2 of them. The first one has to do with the shearing in the fluid, and the second one, it has to do with the contraction or expansion of the fluid. And these terms are certain gradient contributions obtained from first derivatives, in this case of velocity, basically the trace part of the first derivative and the rest. And they come with particular coefficients. These scalar coefficients in general are functions of your temperature, and they're called transport coefficients. They proliferate also at higher orders, right? At higher orders, you can repeat the same analysis, and you're going to also have some scalar numbers appearing there. And these things are going to be higher order transport coefficients. But at this order, the relevant one is the so-called shear viscosity that you saw before, and the bulk viscosity. And in my talk, I'm going to be concerned with conformal fluids, for which this term drops out based on the tracelessness of the stress tensor. And of course, like you can go to higher orders, like it's actually a very tedious exercise. At second order, there are 5 terms appearing in this expansion. At third order, there are 20 terms. And in general, the spirit that I want to share with you, apart from my love for snow, is that such corrections in the stress tensor are very important to understand, to get a handle on. The first reason is that they allow for dissipation, so they break the conservation of this current. Secondly, in principle, in a very naive way, you want to think about equations of motion as related to conservation of the energy momentum tensor. Hence, adding these corrections influence the properties of the solutions of hydrodynamics, right? So it's important to understand them. And like because of these 2 reasons, well, I mean, like it's good to make theoretical progress on them for RIC and LHC physics. So now what I want to do is I want to look at these corrections in the language of the Bjorken flow, and I want to explain to you like how various notions that you saw in a numerical plot showing data from holography, what they have to do with relativistic hydrodynamics. So Bjorken flow is a comoving flow in Minkowski space. As a result of this, the velocity of your fluid is fixed kinematically. You don't have to care for it. I mean, it's given once and for all throughout like the full future light cone. And if you adopt the coordinates that follow the flow lines, then the metric, the Minkowski metric, becomes expressed in curvilinear coordinates, so that there are non-trivial Christoffel symbols. And this generates non-trivial derivatives of velocity, which is, it's given by a fixed vector, but this vector changes as you move from point to point. So these non-trivial derivatives are given on dimensional grounds by 1 over the temperature, 1 over the time, 1 over inverse power of time. And what I want to emphasize is that it's an intrinsically nonlinear phenomenon, right? That we are not talking here about small perturbation on top of anything. Like this is a very nonlinear violent dynamics that, if you want to solve it, say in holography, requires you to solve Einstein's equations in a full nonlinear regime. And now, if you focus on conformal field theories, then based on dimensionality, energy density in 3+1 dimensions is given by the 4th power of the effective temperature, so is pressure. And shear viscosity as a correction, first ordering derivative is going to be the third power of the effective temperature. And if you look at the pressure and isotropy as predicted by the relativistic hydrodynamics truncated at the first ordering derivatives, this is the answer. So it's 8, eta over S, so like the famed ratio of the shear viscosity to entropy density, times the inverse of a product of proper time and effective temperature. And this product, which is the proper time measured in the units of local temperature, or in other words, measured in the units of local energy, is nothing else than this W variable, right? That's why I called it a time variable with this subtlety. And of course, there are higher order terms that are of interest because we're going to talk about asymptotics in this problem. So yeah, I mean, if we go back to this plot, you know, like it's not surprising that, you know, all these curves asymptote the same behavior, because this behavior is simply set by first order viscous correction to your fluid. And there is like an interesting observation that you know, like is important to mention. If you look at, you know, like what is the value of this dimensionless anisotropy in the system at the moment the viscous hydrodynamics becomes applicable, you actually see that it's order 1, which means that relativistic hydrodynamics actually becomes applicable in the regime where the system is still far from equilibrium. And that was something that took the nuclear physics community by quite a surprise. And well, it forced, in particular myself, and I would say also many of my collaborators, to understand it more systematically why it is possible, contrary to expectations, or naive expectations. So in this talk and in other talks, we are about asymptotics, right? So in the end, like what we are interested in is understanding terms with many derivatives of velocity and temperature. So this question is interesting because, of course, like this is a question about, you know, how to properly think in theoretical terms about applicability of relativistic hydrodynamics. And it's also interesting for phenomenology, right? Because, you know, the question is, well, what happens if you start adding terms, second, third order derivatives? Would it improve your prediction? Would it make it worse? What shall we do here? And the key simplifying feature that triggered progress on this problem, view it either as a foundational problem or phonological problem, is the fact that velocity in the Bjorken flow is entirely fixed by the symmetry. That's a very unusual feature. It's not shared by a lot of other flows. Like there are only a handful of other ones that share this feature. And as a result, it allows to define a version of the on-shell gradient expansion of the form of an expansion in inverse powers of W. And this expansion is something that is entirely treatable these days, and also several years back, in terms of standard techniques known to many of you from other applied mathematics or quantum mechanical applications, right? And it turns out that this expansion, the expansion in inverse powers of W, is soluble, without a surprise, in a whole class of models that give rise to hydrodynamics. So if you take any of these models and if you try to get the coefficients in this expansion, what you get is that these coefficients exhibit factorial growth, which means that the hydrodynamic series evaluated on shell, at least in Bjorken flow at this point, has a vanishing radius of convergence. A few years back, there was one particular example of a model that did not exhibit this feature for Bjorken dynamics, but now with one of the papers that I listed in my title page, actually we know that it's a very fine-tuned example, and if we break the Bjorken symmetry, it's no longer the case. So this seems to be really a generic feature. So this was a lesson that probably to all of you is non-surprising at all, but to many people in nuclear physics community was not something that was expected. Because that means that in order to talk about applicability of relativistic hydrodynamics there, you have to bridge with the topic of asymptotic expansions and trans-series and whatever not. So if one is given a factorially divergent series, a standard tool in dealing with it is to perform a Borel transform and then analytically continue it using PADE approximants. And today I had a very interesting conversation with Gerald regarding the physical analogous interpretation of this. But for the moment, let's just view it at its face value. And then if one wants to go from this analytic continuation back to the original function, what one wants to do is the inverse Borel transform. And then what matters for us is the structure of singularities on the complex Borel plane. And of course, there's going to be some singularities because we divide by a polynomial. And we can look them up. This was done first in 2013 and then in a much more refined way by, in particular, Ines and Michal, who are in the audience. And this is, roughly speaking, the picture that you see. So there's a plenty of singularities, and they are associated with branch cuts, with branch points denoted here by various circles and squares. And now, of course, if you want to go back, as I said, to the original variables, you have to perform an inverse Borel transform. But this inverse Borel transform is specified by picking a contour that connects a 0 with infinity. And then depending how we arrange this contour against these singularities, we get different contributions. And in particular, the contribution from this branch cut branch point pair of singularities that appear here are precisely the ones that give rise to the exponentially suppressed and oscillatory contributions to the energy momentum tensor at earlier times. And you can play it more, and you can also seek for signatures of the other things in your signal analysis. So in other words, the relativistic hydrodynamic gradient expansion diverges because of the transient effects that are present in your system that are not captured by it at any truncated order, which also is not surprise to applied math community and people working on quantum mechanical systems with these methods. But in the context of relativistic fluid mechanics, it was something that was generally new. So at least myself, I was coming as an amateur to this field. I was extremely puzzled by this feature. In particular, I was extremely puzzled by the fact that here you have only a discrete set of choices, but from the point of view of signal analysis, you can basically make the coefficient in front of these contributions to be continuous, right? To be anything you want. And then sort of an enlightenment moment came, at least for me, when I was a postdoc at Perimeter Institute, and I heard a talk about applications of these methods to quantum mechanical problems, and I stumbled upon the notion of this trans-series that we have developed with Michal in this context. And in particular, the resolution of all the puzzles I had was that, instead of thinking about the gradient expansion by itself, we have to think about this more encompassing mathematical structure in which basically what you have to do is to sum over all possible exponential terms available to you, with each one coming with its own perturbative expansion, right? So again, like for most of you, nothing really new, but for relativistic hydrodynamics, it was interesting. And now, of course, such a trans-series comes with 3 parameters, the trans-series parameters. In this context, they are denoted by sigma. And the trans-series that I'm showing to you here is not the trans-series relevant for this problem. It's a trans-series relevant to a much simpler problem in which there is basically one exponentially decaying contribution without oscillations. But this can be generalized. In particular, Ines and Michal generalize it to the case when there is oscillation and decay. And then the question, of course, is, we're doing non-equilibrium physics. We're not doing quantum mechanics. Well, there might be underlying quantum mechanics, but we're not doing perturbative expansion in the interaction strength, right? Like we're doing non-equilibrium physics. We're doing perturbative expansion in times at late times. And of course, like what would be the physical interpretation of the transseries parameter, right? And in non-equilibrium problems, of course, we have a notion of initial state. Initial state is much more complex than the late state as viewed by natural set of observables. Like that's what underlies thermalization in quantum mechanical systems. So if we apply the transseries to such a problem, then it is natural to expect that the sigma, the transseries parameter, is going to be related to information about initial conditions, right? And indeed, this is the case. So in this plot that originates basically from this work, we look at some particular non-equilibrium configuration that is denoted here by the red curve. So this is the A as a function of W. We look at the predictions from the truncated first order and second order derivative expansion. So we see that there is a regime where these things don't work that well, and you want to do better. And then the light dashed dotted curve that you don't basically see because it lies basically on top, the red one, is the resummation of the transseries truncated at the second order, so like with m equal 2 included, that basically extremely well over a large range of W's reproduces a non-equilibrium configuration. And the only thing that we have to do is to fit the real part of sigma to represent this non-equilibrium state denoted by the red curve, right? And this is something that you expect to happen more generically in this kind of setups. Good. So, okay, so this is Bjorken flow. So this is a non-equilibrium problem in which resurgent, transseries, etc., everything emerges in the context of time dependence. The time dependence is extremely simple, and sort of like the analog of the perturbative expansion, say, from Ricardo's talk, is an expansion in inverse powers of proper time, or inverse powers of W, to be more precise. And you know, like if one had a choice, one would have wanted to study more rich kind of dynamics without the Bose invariance, with some transverse dynamics. So the question is, you know, how general the structure that was encountered there is. And it's actually a rather hard problem. Like generating the derivative expansion relativistic hydrodynamics, it was achieved, I believe, up to third order included, and it was stopped there because it gets progressively more and more complicated. So therefore, for several years, like this field lacked like a clear organizing principle or like a clear idea how to make progress in this important direction for this field, and somehow like a breakthrough for us occurred around the pandemic time, when we had like much more time to think about these things than these days, I would say. And in a series of works that culminate with these two developments, we were able to provide evidences that actually this factorial divergence is much more generic than we thought it is, or like we can see actually that it is quite generic. So in this model where the transseries has only one exponentially decaying term, this is a model that in the context of modeling dynamics is given by a simple set of partial differential equations. So what you can do is you can put these partial differential equations on some space-time grid. So what I'm showing for you here is a result of the dynamics without really any relevance for nuclear collisions. It's just like a sample kind of a non-equilibrium state that, as opposed to the Bjorken flow, exhibits dependence both on time and the direction along the collision axis, right? So it's a sort of an example of a much higher complexity than the Bjorken flow itself. And in this problem, because the underlying equations of motion are PDEs in two variables, in t and x, and of course in holography you also deal with PDEs, but then like you also have the holographic direction as an additional variable that complicates the problem a lot. So in this case we have PDE in x and t. So everything that we do here on a computer, when we solve the problem on a computer, is just a problem of big matrices, right? we discretize the space, we discretize the time, and eventually, like if we compute derivatives, right, like it's basically matrix multiplication. So because of this feature, we're able, in this class of theories, to come up with a scheme to calculate the derivative expansion to relatively high order. So basically to hundreds and hundreds and thousands of terms. And what you see here is a clear indication that the contributions to the dissipative part of the gradient expansion that you would like to think of as high order behavior of this expansion start exhibiting actually from very early on a factorial behavior. So this is an indication that the feature seen by the Bjorken flow actually proliferates if you break Bjorken symmetry and might be a generic feature of nonlinear equations of relativistic hydrodynamics. There is something quite interesting that might be related to Inesh's talk later today, which is this one. So this one is nothing else than one of these factorially growing curve plotted for large values of n. And what you see here is that there's a factorial growth that occurs over a range of n, but which eventually saturates and gets replaced by a geometric growth. So what we found out is that in this discrete problem, the derivative expansion exhibits a regime of a factorial growth, but because everything is on the lattice and there is an ultraviolet cutoff both for frequencies and for momenta, this ultraviolet cutoff forces upon us geometric growth at large orders. But this is interesting, but we can, in the continuum limit, we can always push it farther and farther to large orders, such that when we take the lattice spacing, we expect that the factorial growth is gonna continue indefinitely. But there is some interesting structure appearing there that interpolates between the factorial growth that might be relevant for all interesting physical applications of the setup and gets replaced by a geometric growth at very large orders. And therefore, like there might be some sort of a way of thinking about the factorial growth in terms of a geometric growth, and we haven't really explored it very much, but I think it's an interesting possibility that has to do with underlying problem having multiple scales. And these multiple scales, I mean here the lattice spacing being the additional one. Good. And there's like one more interesting thing that underlies this plot that I want to say, which is that the derivative expansion in relativistic hydrodynamics and also more broadly is a functional expansion. So we can construct it formally in terms of, like first derivative of velocity, some second derivatives of velocity, third derivatives of velocity, right? But then, the question about its convergence or divergence is not really a question about like this formal expansion, because what you have to do is you have to take this formal expansion and you have to evaluate it on some velocity profile or some temperature profile, or more generally, like whatever your degrees of freedom are. And what basically this plot shows is that the answer to the convergence question about this expansion is not really given in a black and white, right? It really depends on what kind of functions you evaluate it on, right? It's an interesting question that was completely non-apparent to us when we were thinking about the Bjorken flow, but of course, like it's obvious if you think about it from this broader perspective. So the last thing about relativistic hydrodynamics that I want to talk about is something that I'm very excited about, and it comes from this last paper that we wrote. And whatever I've been showing you was basically based on the premise that we generate the derivative expansion to high orders, we isolate the n factorial behavior, and basically we do our analysis. But instead of sort of hunting numerically for the factorial behavior at large orders, following an old work by Dingle, we can postulate that indeed, like the dissipative contributions to the energy momentum tensor scale factorially with a geometric correction that we denoted by chi, and that following this work has a name, the singulant. So this is quite a remarkable formula in my view, because this is a formula in which we do not view the derivative expansion of relativistic hydrodynamics as, like the first term among many with n derivatives, second term among many with n derivatives, but actually we add them together and we view them as sort of a novel, emergent, so to speak, phenomenon that is entirely encapsulated by this n factorial and the chi, with the chi being the interesting part. So the singulant chi can be thought of as an emergent excitation that replaces, in the context of Bjorken flow, this W variable in space-time dependent transseries, right? So something that is much more general than the Bjorken flow. In particular, in this work, we were able to identify such singulants in a number of setups. So in particular, in the setup where there is like a single exponentially decaying thing, in kinetic theory, and also in holography. And we play various games with them, showing that our results are consistent. And the interesting bit, or like one of the interesting bits about them is the following. So I want to encapsulate it in the statement about the meaning of singulants, sort of like the meaning of life. So often when we take a large number of something, so we heard from Ricardo's talk about the large n limit, the description simplifies in terms of new emergent degrees of freedom, right? Like the top limit. And here, what happens in the context of relativistic hydrodynamics, and I want to view it more broadly in the context of effective field theories, a sum of a large number of different gradient terms reorganize itself in terms of a simple singulant description, right? So instead of thinking about very, very many terms, individually, we want to add them together, all with the same number of derivatives, and view them together in terms of this simple expression. And in fact, the factorial ansatz under like the singulant ansatz, what it does, it leads to a linearization of the problem and reveals a new duality between the large order behavior of the hydrodynamic gradient expansion and the linear response theory. There is a way to make it precise. I don't want to get there. It's described in detail in the paper, and I think it's quite interesting. Yeah. So in the last 10 minutes, as asked by Gerald, I want to sort of step back a bit and try to discuss this result in somewhat broader context and try to signal some of the things that I think might be exciting to explore for me, maybe for my collaborators, and hopefully also for some of you. So, of course, like the first thing that I want to talk about a bit are singulants. Like that's the latest contribution to relativistic hydrodynamics in the context of asymptotics. So there are, very many actually questions of varying difficulty and of physical or mathematical relevance that can be answered and should be answered in this context. So as I try to indicate in Bjorken flow, the information about non-equilibrium initial states gets encoded in transseries parameters. Here the presence of singulants indicates the existence of a more general transseries structure. And the natural question is, when we have these singulants fields, there are fields now, right? Like they depend on time and space. So how the non-trivial initial states that we consider that lead to non-equilibrium evolution basically map into initial conditions for singulants, right? It's a very interesting question. It's about basically it's about structures appearing in non-equilibrium dynamics. We don't know the answer to this question, apart from the known case of the Bjorken flow that is no longer that interesting in this context. Of course, the singulants are interesting because via resurgence they are related to exponentially suppressed contributions that exist on top of relativistic hydrodynamics. And the lore that we developed in the course of the past decade is that hydrodynamics becomes applicable when exponentially decaying terms become negligible, physically negligible. So since the singulants are supposed to appear in exponences, right, like what structures sitting in excellence, what they tell us about the estimates for the times of applicability of hydrodynamics. And it's an interesting question, right? Because the answer might depend where you are in space-time, right? That's something that might have some rich underlying physics. So of course, I motivated this talk, and my interests have been largely driven by the physics of nuclear collisions at RIC and LHC and the QCD physics there. But of course, relativistic hydrodynamics has a wider scope of interest, and hydrodynamics also it's an overwhelming framework behind many things. So one can ask a question about physical relevance of singulants beyond what I showed you. In particular, if one has a turbulent flow, if one has a cascade of energy to the UV, which probes shorter and shorter wavelengths, like does it excite in some way these singulants, degrees of freedom, etc.? I think these are very interesting questions that deserve attention. One thing that I was completely vague about is the notion of ambiguities in derivative expansion, right? So it turns out that derivative expansions are largely ambiguous. We can change the form of terms in the derivative expansion by doing field redefinition. So for example, some of you who are familiar with higher derivative gravity know that you can get rid of some terms in favor of others, etc., etc. And roughly speaking, similar things occur in relativistic hydrodynamics. So one question one may have is how this different expansions affect give rise to different singulants, and how to go back and forth between them, right? Like, is it that there is like a one trans series that we can transform into other version of it without changing the physical context, which is what I would expect, or this story is much more subtle? I don't know. And related to it, of course, this is a space-time dependent trans series, right? How to resum it, what to do. And of course, like more broadly, relativistic hydrodynamics is an effective field theory. So, well, can we apply singulants into effective field theories of high energy physics, and what we can get there, what we can gain by it, what we can understand. So changing gears in the context of thermalization in high energy physics, a very interesting notion that appeared in the course of the past 15 years is the notion of a non-thermal fixed point. So of course, I just have a few minutes, so I'm not in a position really to explain to you what the non-thermal fixed point exactly is, apart from saying there is a situation in which a quantum field theory, relativistic or non-relativistic, undergoes non-equilibrium dynamics. And as captured by simple observables, such as 1 or 2 point functions, it exhibits self-similar behavior. So in general, a 2 point function, this is an equal time 2 point function, is going to be a function of time and momentum if you are in a translational symmetric situation. But around the non-thermal fixed point, the 2 point function becomes expressed not as a function of, say, 2 or 3 variables, but as a function of 1, with all the remaining information encoded in the scaling exponents, right? The non-thermal fixed point is defined by a situation where the scaling exponents are time independent or constant. But of course, if you look at earlier times, there are corrections. And in particular, there are parallel corrections to these scaling exponents, as we know from the works that appeared earlier this year. But now, also because of the work that I wrote with Jürgen Berges and Timo Price in September this year, we know that there are exponential in T contributions to the 2 point function. So we have a parallel, we have an exponential, and of course, a natural question is, does trans series underlie also this non-equilibrium example, and can we get a better understanding of non-thermal fixed point using methods that are standard for many of you? And the last thing is perhaps the most speculative and has the least to do with relativistic hydrodynamics, but I'm interested in this topic, and I think there might be something interesting to be done there. So this is a picture of a black hole spacetime with ADS asymptotics. And in the course of the past almost a decade, there's been an enormous interest in the question of what is the physics of volume in gravity and in quantum gravity. So in quantum gravity, there's been a lot of attention devoted to the areas, right? Like going back to pioneering works by Hawking and others. about area theorems, et cetera, and Bekenstein-Hawking entropy. But in gravitational theories, there are also volumes, right? Like the volume of the whole spacetime or volume inside the black hole. And in the latter context, starting with the works by Lenny Susskind and continuing with many other developments, it's been noticed that there is a way to, define a black hole volume that naturally captures a very puzzling feature of black holes. That is, like, if you calculate the volume inside the horizon, this volume exhibits persistent linear growth. And then, for reasons that I don't have time to really talk about, Lenny Susskind and other people sort of conjectured that this persistent linear growth, after time exponential in black hole entropy, so a very long time, should saturate. And basically last year in the summer, there was a very interesting and I think important paper in which, in the context of JT gravity, understood as a matrix, double-scale matrix integral, these people came up with a quantum version of a volume for two-dimensional black hole. And they showed that indeed this quantity saturates at times exponential in entropy using techniques standard now to quantum JT gravity. So you see here persistent linear growth followed by something that is going to be a saturation. So this is another problem from high-energy physics that at its face value has nothing to do with relativistic hydrodynamics, but that also exhibits a change in the behavior in time. It includes terms that have sort of like different rates of growth. So I cannot sort of resist but ask, can we understand this result better using asymptotic analysis and learn something new in this context? So let me summarize my talk. Around 2010, so a bit more than 10 years ago, we learned from ab initio studies of quantum field theories, including holography, that relativistic hydrodynamics can apply far from equilibrium. And this called for rethinking how to understand relativistic hydrodynamics in theoretical way. And in my talk, I describe understanding of this set of theories of these phenomena based on trans-series that we gained in the course of the past decade, including many works by the people in the audience. And the thing that I'm particularly excited about is the development from the past 14 months, which is going beyond Bjorken. So I'm talking about first results in the presence of space-time dependence and first results about singulance in relativistic hydrodynamics. And I want to finish this talk on a positive note, which is that there are many interesting questions on at the intersection of asymptotics and non-equilibrium high-energy physics. Of course, one of them is developing the field of singulance in this context, understanding non-terminal fixed point using asymptotic methods, and of course, maybe even looking at complexity dynamics, right? So this recent development from last year. So that's all I wanted to say. Thank you very much.
Thanks for the interesting talk. I was interested in your graphs on the singulant.
Mm-hmm.
Is that found by fitting? Are you computing coefficients and then trying to find the chi function?
Yeah. So there are two layers of it, right? So this is a numerical study. This is the Borel plane, and here what we do is we do two things. So one thing that we do is basically we have here two singulants that exchange the dominance depending on where you are in time. And what we get from the microscopic description in this case is an equation of motion that the singulant obeys. And of course, we can solve this equation of motion and we can predict how it's going to move on the Borel plane at later times at, say, the same position, right? And this is the prediction that we have. That is basically analytic. It's based on solving an equation that we know analytically, right? With an input from the Borel plane at a given time, right? And then numerically, this is what we get. And you see that it lies spot on each other. So there's a mixture of numerics and analytic understanding that go hand in hand together.
And you mentioned these kind of open problems about initial conditions for the singulant, but here it seems you knew what those initial conditions were.
Yeah, well, so here it's the thing is that here we look at the initial condition is really very naively taken from the behavior of the Borman plane at earlier time, right? And you just look how it looks like at later times. And this is also a problem in which the singular equation of motion gets highly simplified, right? What I have in mind is to be more systematic and say, what kind of information about the initial condition define that, arbitrary initial Cauchy slice, how it gets translated into the behavior and maybe number of singulants that you have in your problem, right?
Thank you.
That's not understood. Yeah, thank you for the question.
Anybody else?
Can I take a look at the figure of the Borel singularities for the 1 over W expansion? I think the previous, or much more.
You mean this one?
Okay, yeah, that one. So I may have missed the point maybe, but so it is Borel summable, right?
Yeah, you might say so, I guess, yeah.
So can you, so I wonder how you can judge whether these Borel singularities can contribute to the exact results. So you can find out how to figure out.
Good. Thanks for the question. So, I'm not sure if this is controversial or not, but for me, always the Borel summability was sort of a red herring in a sense that I always wanted to think about the trans series being the relevant object.
Okay.
And now, in particular, the Borel summability means that I can align my cut along the real axis, right? But more generally, I don't think there is physics to it, right? I can align it differently, and I can compensate for this difference by changing the trans series parameter in a way aligned with the cut. So personally, I don't think it's the Borel summability is relevant here. In general, the trans series is going to have a sum over all these objects, right?
Yeah.
And of course, the question is if you can in your non-equilibrium dynamics in the kinds of initial states that you consider, if all these objects come with free coefficients related to initial conditions. And that's an interesting question, but Borel summability, I think, is at this level a red herring.
Physical reasons, maybe.
Yeah, so actually there are physical reasons for it. As I tried to draw here, the coefficient here at the position of this cut, the position of the branch point is intrinsically related to this exponent that you can identify. Here even with your naked eye, right?
Yes,
and then you can do a more refined signal analysis methods, perhaps using methods like PRONI. That allow you to isolate harmonic dependence in your signal, and then you can try to identify the other terms. Of course, there is an underlying reason why I put or whoever made this plot put these triangles and squares and dots, and the reason is that we have expectation what kind of singularities they would be. In this case, in this particular case, they are related to non-hydrodynamic quasi-normal modes at zero momentum. And in the singularant paper, we argue that this is not really what's happening generally for these trans series, and we explain why. So in this case of asymptotic understanding of relativistic hydrodynamics, sort of the theory of non-equilibrium phenomena goes hand in hand with the asymptotic analysis. So often we know like what to expect. There is one case that I think is very puzzling still to us. That was a subject of a paper that myself, Michal P, and a few other people wrote, which has to do with kinetic theory. There we found singularity. We found like similar plot, but we found a situation in which there are singularities that do not seem to have any physical meaning in terms of non-equilibrium degrees of freedom. But we understood, where they originate from, but we don't understand like what they signify physically or maybe not. So this is something that I would be happy to talk to you in private if you're interested.
Thanks so much. Now I've got a point.
Yeah, thanks for the question. Yeah.
Thank you for the nice talk. Can you go the slide forward?
The slide forward.
Sorry, backwards. The one where you were writing the... Excellent, thanks. Yeah. So you mentioned... No, the one...
This one?
What is it, 7? Yeah, please. You mentioned that this is generic, the factorial growth, but you also mentioned of a case where you actually don't get factorial growth. Is there a sort of symmetry that prevents you in that case from getting divergent series? And secondly, are there also exponentially suppressed corrections, even if there is no factorial growth? Because there are supersymmetric cases in which you get a convergent perturbative expansion, but you also get non-perturbative corrections.
Yeah, so to the question about the symmetry, yes, like the symmetry is the Bjorken flow symmetry, so the boost invariance. If you break the boost invariance, you start seeing in the same setup factorial growth. Regarding exponentially suppressed terms, my first instinct would be to say no, but maybe my co-authors know it better. So can you confirm, or you? Yeah? Yeah. So I think like your intuition was correct, yeah. Yeah, yeah, thanks, Alex. Yeah.
Thank you. One question about these discrete phenomena that you mentioned, like on the next slide, I think.
Yeah, like this thing. Or
no, not this discretization issue, but in the beginning you mentioned that you find like discrete in the slide that you had actually before, like the one with the maybe the second one or slide number 2, this one exactly.
Yeah.
So you mentioned that there's a discretization in these waves on the right-hand side. So can you comment a bit more on this, if they are associated to these poles in the Borel plane, or if they are more connected to the dynamics, and how they are connected to these singularity structures?
Mm-hmm. Yeah, good. Thanks for the question. So what I had in mind is that there is a branch cut here, right? So like you're gonna get a contribution depending on how you go around it, right? And this contribution, I don't view it as a physical contribution, right? Because it's related to ambiguity on how you resum your series. But what I've tried to argue is that the trans-series parameter has also a freedom that you can use to compensate for ambiguity in in how you go around the cut. So in particular, I mean, the thing that took probably like the most of the time to understand conceptually in this paper, at least for me, was to precisely understand that there's this compensation mechanism underlying trans-series that for sure is part of mathematical physics literature, but it was just hard, at least for me, to get the point. So this discrete ambiguity is just the way one deals with trans-series in the way that we represent it. The physical ambiguity is continuous, at least I would like to think that it's continuous, and is related to what we pick as a non-equilibrium state. And in the context of this particular model, this quantity A obeys a first-order ordinary differential equation. So therefore, like in order to initialize it, you have to specify its value at the initial time, right? So there's a whole range of values that you can specify, none better than the other, so to speak. And this range of values gets mapped into the choice of basically the real part of sigma. And that's the continuous freedom that I like, because it's physical. The discrete freedom is a way how you deal with resummations.
I see, thank you.
Thanks.
Any other questions? Okay, let's thank speaker again. So in principle, lunch is outside somewhere there today. In the next 3 days after today, they'll be over in Churchill College, but today it should just be outside here. And we start again at 2:30.